Good morning, everyone. So at Mobileye, we are working on the spectrum from driving assist, the technologies for avoiding collisions, front-facing camera, sometimes fusion with the radar, interpreting the visual scene, and doing all the actuations in order to avoid collisions. And that's one end of the spectrum. The second end of the spectrum is the future launch of autonomous cars. We're talking about level 4, level 5, where you can have cars that can drive on their own without any human assistance. So when we think about autonomous cars, normally we think about the technology that powers all the sensing, the computer vision, the artificial intelligence, the high-performance computing, the communications. What kind of car platform do we need? Do we need cars with powered electrically? What kind of redundancy in terms of hardware, redundancy in steering, redundancy in braking? But there are other two areas that are very, very critical that we believe that without them, we're not going to see autonomous cars. One of them is economic scalability, being able to design this kind of technology that powers autonomy in a way that can be manufactured in volumes of millions of cars. And this is something deep. It's not only relevant to what kind of silicon you need in the car. It influences your entire thinking about what kind of algorithms, what kind of software stack, what kind of redundancy, how do you test it, how do you build maps, how do you update maps. It's really very, very deep, this issue of economic scalability. That's one area I'm not going to cover. The second area is fundamental. The second area is about safety. What kind of guarantees can we, the manufacturers of the technology, give society in terms of safety? And we know that society is very, very sensitive to fatalities that can arise from technology. Society is much less sensitive to humans killing humans, but is very, very sensitive if computers would kill humans. And we see that from every small minor accident between a test car and a human creates so much media attention. If we cannot say clearly what are the guarantees that we are providing, this would be a communication nightmare and could kill the entire industry. So when you start thinking about safety, that there are certain issues that you immediately get stuck with, and then I'll start immediately with them. So what I'm going to cover is a paper that we published about half a year ago to start a conversation. It's a very technical paper. It is how to guarantee safety. But what does it mean to guarantee safety? And the first thing that we started, when you start thinking about accidents, it's really impossible to guarantee that there will be no accidents. And what you see here on the left-hand side, you see the autonomous car, the blue car, surrounded by red cars. And you see that this blue car is simply trapped. If a red car hits him, there's no way that the blue car can escape. So to say that the blue car would never be involved in an accident is simply impossible, because there are other agents on the road, human-driven agents, and those will behave as those will behave, and sometimes it's simply impossible to escape an accident that's coming upon you. And you cannot prevent the situation, because this kind of configuration happens all the time. When we're driving on a highway, there are cars on our left, on our right, beforehand, on our rear, and we could be in this kind of situation. And preventing the situation is not practical. So stating that there'll never be accidents is something that is impossible. And then the question is, if absolute safety is impossible, what do we really mean by being safe? Right? And I'm steering this toward a technical discussion, not a philosophical discussion. I think that the ethical dilemmas can be couched in the context of what I'm going to describe, but the purpose here is not philosophical. The purpose here is technical. How do we employ science in order to answer this kind of question? And this is the task that we set out to do in the paper that we published half a year ago. So when we look at the current approaches, there are basically two approaches. One is the statistical approach. And there is this claim that self-driving cars should be statistically better than a human driver. Now, what does it mean, statistically better? If we start thinking about it, well, the known statistics about human fatalities in driving is that the probability of a fatality per 1 hour of driving is 1 to a million, 10 to the minus 6. This is the known statistics. So with these statistics, the number of people killed on road accidents in the US is about 40,000 people. Okay? Now, what does it mean to be statistically better? Are we going to say that computers would kill 30,000 people instead of 40,000? It will not work. It's going to kill 10,000. So to be statistically better, you need to be orders of magnitude better in order for society to accept it, not 2 times better. So if we'll be 1,000 times better, we'll go from 40,000 to 40, maybe society will accept something like this. So we are basically talking about a desired probability of a fatality per 1 hour of driving to be 10 to the power of 9, 10 to the power of minus 9, 1 to a billion, in order to be really much, much better for this statistical argument to hold. So now, once we understand what is the probability that we're targeting, now we come to computer science, and you can prove the following claim, that if you have an event that occurs at a very, very small probability p per 1 hour of driving, the amount of data that you need to collect in order to validate is 1 over p. So if p is 10 to the minus 9, 1 over p is 10 to the power of 9. Now, 10 to the power of 9 hours of driving, let's say in an hour of driving we drive 30 kilometers, we're talking about 30 billion kilometers. So this is clearly out of the scope of any actor in autonomous driving in terms of collection of data. When you start reading about other actors that are playing in this field, they are collecting 3 million kilometers, 4 million kilometers, 5 million kilometers, right? Just statistical arguments say that you need about 30 billion kilometers. The other problem with the statistical argument is that it's not transparent. When an accident will happen, all what you can say is that I statistically validated the technology and the probability of an accident is 10 to the minus 9 and I'm fine. But will society accept something like this? A non-transparent model of safety. And this is also something quite tricky. We may end up with a situation in which society will not accept something like this. You would like to have something that is explainable. If we killed someone, at least let's explain why we killed this poor person. Okay? The other approach, we'll call this the best practice approach. So the best practice approach, if there is such an accident and I'm the manufacturer of technology, I come to court, and my line of defense would be, well, I'm the best in the field. In every element of the technology, I have the best technology. I have the most number of sensors. I have the best sensors. I have driven the most mileage in terms of validation. I have the best simulators, and so forth and so forth. So in any element that you choose, I'm the best. So if you are penalizing me, you're basically penalizing the entire industry. And this is what you want to do. You want to penalize the entire industry. So this could be a reasonable line of defense, but what it leads to an over-engineered solution, because it's kind of a race, an arms race. My competitor added another sensor. I need to add another sensor. And eventually it will not guarantee any safety. Simply an arms race of technology without any guarantees of safety, and we're still not transparent. We cannot explain why that person was killed or injured in an accident. So our conclusion that both approaches are not the right approach, and we need to think about this differently. One inspiration that we started with was the way autonomous emergency braking, automatic emergency braking is tested today. So automatic emergency braking, you have a sensor front-facing, a camera or a radar, or both of them working in fusion. And the sensing element detects the road user in front, could be a pedestrian, could be a vehicle, measures the time to contact, and actuates the alarm, and then actuates the brake in order to avoid collisions. Now, there are two parameters that you need to optimize. One is false negative, the other one is false positive. The false negative is the probability of not actuating when you're supposed to actuate. There was a vehicle in front, you're about to hit it, and your system did not actuate the brake. This is false negative. False positive is the opposite. The system actuated the brakes when it was not supposed to actuate the brakes. Now, when you look at regulatory bodies, they test only the false negative. What does it mean they test the false negative? This is something you can do in a test track. You create a scenario where, for example, you have a vehicle in front, sometimes stationary, sometimes moving, or a pedestrian, a mannequin, stationary, moving on the side, and so forth. And the car that is being tested should drive at a certain speed and actuate the brakes as expected, and it's done over and over and over again, and you have to succeed, I don't know, 80% of the time or something like that. So what are you basically testing is the false negative. And it has to pass a certain threshold in order to approve the technology. But the regulator is not testing false negative, a false positive. And there are two reasons why you don't test the false positive. One is very, very difficult to test because you need real-world data. You cannot just drive in a test track and say what is the false positive probability. You have to drive in the real world, and you have to collect millions of kilometers of data in order to get meaningful statistics. This is something too big for a regulator to start managing. The second is that you don't need to do it because it is in the interest of the manufacturer to make sure that the false positive would be close to zero. Because if a driver is driving the car and the car all of a sudden applies the brakes without any reason, there was no danger, there was no other road user on the road, it's simply a mistake, a false positive, that customer would take the car back to the dealer and would not want to do anything with this car, and would not want to do anything with this car manufacturer as well. So it is in the interest of the technology supplier, of the car manufacturers, to make sure that the false positives are almost zero. So what the regulator needs to test is only the false negative. Okay? So this is kind of the inspiration is that from a regulatory standpoint, you don't need to test everything. You need to test what is really important and leave the other elements that are in the interest of the suppliers to test for themselves. And the question is how do we take this inspiration and shift it to the area of autonomous driving? So the approach that I'm going to kind of highlight in the next few slides, and then I'm going to show you examples, also examples from our test fleets, autonomous test fleets. So the goal is that self-driving cars should never be responsible for an accident. I said absolute safety is not possible to guarantee, but we can guarantee that our car would never cause an accident. Okay? So self-driving cars should never cause accidents and should properly respond to mistakes of other drivers. Those are kind of the two areas that we want to guarantee. So this is why we call this responsibility safety, responsibility sensitive safety. So we need to describe what does it mean to be responsible. So there are three questions that one needs to tackle in a scientific way. One, what does it mean to be in a dangerous situation? Now, when you think about it, this is ill-defined. It's not defined today. So for example, if I drive and I change lane and I cut another vehicle and that vehicle hits me, we'll go to court. I will claim that the other driver was sleeping, texting, talking, not focused on the road, and he should have slowed down. The other guy would claim that I did a reckless cut-in. Okay? Now, who's right? Well, there's going to be a jury, there's going to be a judge, skilled set of the lawyers, and so forth, and a decision would be made. This is exactly what we want to avoid here. We want to define things in a formal way, because today, this is not well defined. What does it mean to be in a dangerous situation? Second, what is the proper response when you are in a dangerous situation? How do you respond properly in order to get out of a dangerous situation? Once you answer these two questions, then you can answer the question of who's responsible for an accident. Clearly, the party, the agent that did not properly respond is responsible for the accident. And then once we answer these three questions, we can design an algorithm that will make sure that an autonomous car would never get into a dangerous situation, and if it gets into a dangerous situation, it will always do the proper response, therefore it will never cause an accident. This is the kind of goal that we are reaching here, and basically what we want to do here is to set the rule of the game in advance, and not after the accident go to court and start with all the biases that people have in analyzing cases to go over it. Is that because we're talking about machines are precise, we can set these definitions in a precise manner, and then have a conversation with regulatory bodies to start adapting these kinds of definitions. So just the scope of what I want to show here is that we look at the Sense, Plan, Act methodology, where sensing is understanding the surrounding using sensors, cameras, radars, laser scanners, high-performance computing, artificial intelligence. You want to understand the surrounding, that's sensing. Planning is all the decision-making. I want to change lane, now I need to merge, two lanes are merging, I need to negotiate with other road users. All of this is called planning, and acting is the actual actuation. How do I move the car according to what my desires were, what my planning desires were? So RSS deals with safety of the planning module. We're not dealing with the sensing module, and I'll get to that at the end of my talk. We are assuming here that sensing is perfect. That means the system understands its surrounding. It knows where other road users are and makes the measurements correctly. And it's now a matter of planning. We need to negotiate with other road users. How do we plan under guarantees that will never cause an accident? This is what, and this is also the most difficult part, because not only it involves negotiation, it's a closed loop kind of thing. It means we interact with the environment environment interacts back with us. It's not something that we can do offline in terms of offline processing like you can do with the sensing. And dealing with the simulators would not solve the problem, because the task of proving that the simulator reflects reality is more difficult than the task of autonomous driving. So we'll basically end up with the same problem. Okay, so the idea is to reduce the complexity of driving into four simple rules. So what is our attempt? Our attempt here is to formalize in a mathematical sense the common sense of driving. Because driving is not just following a set of rules. Driving, there is human judgment. You need to be careful. What does it mean to be careful? For example, you have a right of way. Right of way is given, it's not taken. Now, all of this is kind of common sense of driving, and we want to formalize this. So we'll start with rule number one. If you are hit from behind, it's not your fault. But rule number two, if you are hit from behind because you performed the reckless cut in, it is your fault, right? So we have to kind of balance between rule number one and rule number two. Rule number three, this is the common sense of driving, that the right of way is given, not taken, right? Because if there is an accident, even if I had the right of way, but I didn't behave carefully, I'm still responsible. For example, I need to pass a traffic light and I have a green light, so I have the right of way, but there's another car stuck in the middle of the junction because of whatever reason. Maybe that car even passed through a red light. If I hit that car, it's my fault, right? Because I had to be careful, right? So right of way is given, not taken. And rule number four is where you have occlusions. So areas of limited visibility, you need to be careful. And we need to define what it means to be careful when we have limited visibility. And surprisingly, all human judgment, the common sense of driving, can be reduced to these four rules. So in setting up a model, we have there are two things that we need to prove to ourselves. One is soundness. We want this model to reflect human judgment. That means if this model clears the blame of an agent, we expect human judgment to agree with it. If the model does not, if the model clears the blame, but human judgment says, no, that agent is responsible, then something wrong is with the model. So we want the model to be sound. It has to reflect human judgment of the common sense of driving. The second one is a bit more tricky. The second one is usefulness. We can always create a model in which everything is safe, but we're not moving at all. Right? If I simply don't move, there will be no accidents. Or if I move very, very conservatively, maybe there will be no accidents, but then I'll be blocking traffic. Right? The challenge in all of this is, on one hand, not to obstruct the traffic flow, means to drive assertively. So, for example, our testing in our autonomous fleet is multi-site, but one of those sites is Jerusalem. I don't know if any of you visited Israel or visited Jerusalem in particular. If you are not assertive, stay at home, right? You cannot drive there by assuming that others would vacate the road, give you space, allow you to merge. You need to negotiate, and this is serious negotiation. If you are too defensive, nobody will let you drive. So, do we want to exclude cities like Jerusalem for autonomous driving? So what would be left? Mountain View. That's it. So you need to be assertive. So on one hand, you need to be assertive. On the other hand, you need to guarantee safety. So usefulness becomes a big issue. You want a model that allows assertive driving. Then there is the issue, kind of theoretical issues about usefulness. For example, there could be butterfly effects. It means I'll be making an innocent action now. There's going to be a chain of events, and then far into the future, an accident is going to happen, and then you can trace that accident to my innocent action that I did right now. If a model has a butterfly effect, it's not useful, because then from a computational point of view, I can never validate the proper response. So we need to build a model in which my decision makings are local, and you can guarantee formally that there's not going to be any butterfly effect. Another thing is when you go and validate your proper response, is it a star kind of relationship? It is me checking every road user separately, my relationship with every road user separately, or is it me checking all the possible combinations, pairwise, triple-wise, quadruple-wise between me and all other road users? If it is the latter case, from a computational point of view, it becomes unwieldy. It becomes non-useful. So the usefulness is not just a title. It is critical. If you build a model that doesn't follow the usefulness criteria, then it is literally useless. Okay? And so when we build this model, on one hand, it needs to conform with human judgment, how to formalize human judgment, and the other one has to be useful. So it starts with the idea of defining what does it mean as a safe distance, and both longitudinal and lateral. Then defining a situation is dangerous if both the lateral and longitudinal are non-safe. So if there are two vehicles and the distance is too short, we have a longitudinal non-safe distance. If two vehicles are too close to each other, or one is cutting each other, we have lateral closeness, and you have to have both in order to say that you're in a dangerous situation. And then there's a definition of what is a blame time. It is the moment that one of those longitudinal or lateral broke, you breached the minimal distance. And then there is a proper response, depending which broke first, the longitudinal or lateral. You need to have an actuation, which is either longitudinal braking or lateral braking, in order to get back to the safe state. And then responsibility is the agent that did not respond properly. So this is kind of the idea. And I'll show you a few examples. I'll try not to make this too formal. Anyone who's interested can go and read the paper. But when we look at lateral, so there is kind of a lateral safe distance that I'll define later. And blame time is when the two lateral corridors are colliding, and then the car that breached this lateral corridor needs to brake laterally in order to make a proper response. So this is very intuitive. If we have a non-safe cut-in, so what this means is that the lateral corridor started to collide. So the red car that initiated it needs to brake laterally, but also the yellow car needs to brake mildly. And this is part of the common sense of driving, is that you need to be careful. It is true that you are not responsible for the other guy that is making a mistake, which is a non-safe cut-in, but if you can be careful, you should be careful, and this case means that you need to stop mildly, to brake mildly, and the question is, how do you formalize this? And then if we have a longitudinal breach, then the yellow car should brake longitudinal in order to get back to the safe state. And the question is, how do we find what is this longitudinal distance, this minimal distance? I'll come to that a bit later. If we have oncoming, then in an oncoming situation, one of the cars is not driving in its lane. So let's assume that it is the red car not driving in its lane. So the red car, once we got to the blame time where those two longitudinal corridors are intersecting, the red car should blame strongly. The yellow car should blame mildly because the yellow car is in its lane. Okay, this is also quite intuitive. And when you talk about responsibility, if the red car, which is in front, brakes for whatever reason, and the blue car hits it, it is the responsibility of the blue car, because it means that the blue car did not maintain safe distance to the red car. And that's going to be part of the definition of what does it mean to create a safe distance. The same thing with a lateral collision. Okay, it's not the responsibility of the red car if the blue car breached the lateral safe distance, but in some cases it could be both. Responsibility could be shared. So when you start talking about safe distance, let's think about the longitudinal safe distance. We define 4 parameters. One parameter is the response time. So response time meaning that once, say for example, the car in front of me applied the maximum braking, there is a certain period of time in which I'm not aware that something is happening, even if I'm a machine. There are delays. It could be much shorter than a human response time, but still there is a response time in which I'm not aware. During that response time, I could take the worst case assumption and assume that I'm doing a maximum acceleration. So during the response time, not only that I'm not slowing down, I'm accelerating. It could be 0.1 second, but still, in that response time, I'm accelerating. After that response time, I'm applying brakes, and there are 2 parameters of deceleration. One is the maximum brake, which will happen to the front car, and one is the minimum brake, which is, so for example, the maximum brake could be 1G, the minimum brake could be 0.5G, which is what kind of brakes is reasonable for me to apply in order to avoid an accident. And then you can put all of that, since we're talking about kinematics, you can put all of that in an equation and get a number which is this distance. What is the minimal distance such that if this car in front applied maximum deceleration, there was a period of response time. In that response time, I did maximal acceleration forward, and then I applied minimum deceleration, I will stop without hitting the car. Okay? And that will give us the distance. You may think that these distances, because of this response time at the maximum acceleration, that these distances will be big and will create a grandmother driving kind of situation. No, they are very, very short. They are so short that you as a human driver would not drive so close to the car in front of you. Okay? So it is, the numbers that come out are very, very reasonable in terms of allowing assertive driving. And then the question is, what are those numbers? So in our test cars, in our technology, we set up those numbers. What we believe should happen is conversation with regulatory bodies, with industry actors to set these numbers, to set what is the response time, what is the maximum deceleration, what is the minimum deceleration, what is the maximum acceleration during response time, that we all agree, that the entire industry that manufacturers autonomous cars would agree on those numbers. And this is exactly what I meant is defining what is a dangerous situation is something that is lacking. And here's just an example of just simply defining what does it mean to have a safe distance in the car in front of you is something that we all need to agree on. Okay? When you talk about lateral, it's a bit more tricky because you can think of a situation in which there is a lateral movement, still the corridor is not intersecting, and now the blue car moved 2 centimeters to the right, and now is intersecting. Now, is the blue car now violating the lateral? No, because you cannot really assume that lateral distance would be stable all the time, because people fluctuate. So you need to robustify this with what is called in computer science margin. You add a margin such that you allow for fluctuation in the lateral distances. Okay? Another thing is related to route priority. So the blue car has the priority. So the blue car is driving unimpeded, and the red car should do the calculations such that it can stop in time before crouching to the route priority. But now what happens in this kind of situation? So the blue car has priority, so he has the right of way, but that right of way is not given to him. So the blue car needs to do the calculations of safe distances, and there is now a definition of ordering. Who comes in front of what? And there is a formal definition of ordering, and if the red car is in front in terms of the ordering definition of the blue car, then the blue car, even though it has the priority, even though it has the right of way, should do the safe distance calculations such that if the red car doesn't give the right of way, it can still stop and not hit the red car. And all of this is defined formally. I'm showing you the kinds of ideas that you need to cover in a formal way. One also needs to cover this kind of situation in which the red car is encroaching and the blue car is going to overtake and move here. When this can happen, how this can happen, and how do you guarantee that this happens under all these safe distances calculation. Then there's the reduction of this priority idea to traffic lights. So with traffic lights, the car that has priority depends on the color of the traffic lights. We can then extend this to places where you have unstructured roads. Either you don't have lanes, like in a parking lot, or the geometry is clear, but there are no lane marks, so you don't know which lane is what. The idea is to use the car heading as creating the geometry, and then use all the definitions that were before. In case of pedestrians, this is a reduction to route priority. In most cases in urban roads, the pedestrian usually has priority, but in some situations it doesn't. For example, when you have a traffic light, there's a green light for the car, there's a red light for the pedestrian, the car has priority. So all of that can be reduced. Many of this complicated situation can be reduced to issues of priority. And then we have a detailed analysis of what happens with occlusions. What does it mean to be careful under occlusion? There are assumptions of what is the maximum speed, which is V limit, of the object, could be a pedestrian or a vehicle, that is coming out from an occlusion boundary. And that number needs to be set again with industry players, with regulatory bodies. What is that V limit? Is it the legal driving speed, plus 20%? What is the V limit, so that you can calculate what is the speed that you are arriving and encroaching outside of the occlusion boundary. So in terms of soundness, so there is kind of a set of definitions, and now the question is this sound? How do you go and prove that it is sound? Now this is tricky, because we are formalizing human judgment. So how do we prove that we actually formalized human judgment? So the way we looked at this now from a data point of view. There is data around. We started with the NHTSA crash typology. So what NHTSA had, they took 6 million crashes and divided them into 37 scenarios. And all of this is publicly available. We took those 37 scenarios and we ran them through the model. Again, soundness is that if the model clears the blame of an agent, human judgment should agree with it. Yeah? And all those 37 scenarios passed. There are all sorts of scenarios from Portland. We are now working with other agencies like the EU Commission to get additional scenarios and running them through the model to see if we are violating the soundness. And if we are, then we'll make modifications. But so far, we haven't seen any situation which violates the common sense that we have in our definition. But this is an ongoing thing. I'm not saying that we're never going to find a scenario that violates the definitions. If we do find, then we can go and update the definitions. In the case of usefulness, as I said, this is non-trivial because there might be a butterfly effect. And we prove that under these definitions, the way we set them up, there's no butterfly effect. And we can use the induction principle to prove that. And then there's the computational efficiency, is that the analysis that we need to do is only a star-shaped. The AV car comparing to each road agent separately. What is the safe distance, longitude and lateral to each road agent separately, and you don't need to get this compound effect of what is my relationship to pairs, to triples, to quadruples, and so forth. And we prove in the paper that both of these are satisfied, so you have something that is, so one of the major claims in the paper that the driving policy is the planning part that complies with this RSS proper response, the definition of proper response, is guaranteed to never be responsible for an accident, and the proof is based on the induction principle. So again, so we're talking about an effort, scientific effort, to provide guarantees, not to provide probabilities, but to provide guarantees. And what I'm claiming here is that under those sets of definitions that so far we believe are sound, and we prove that they are useful from a computational point of view, if you satisfy these definitions, your planning module would never cause an accident. This is where we're going. Okay, and so how do we use this in order to validate an autonomous vehicle? So now I'm going back to the inspiration of the AEB, the automatic emergency braking, where the regulator tests the false negative and does not test the false positive. It assumes that the manufacturer of the technology, which is the car maker, would make sure that the false positive is going to be zero because it's in the interest of the car maker to make sure that the false positive is zero. So how this maps into what I've shown so far. So I'm saying that what the regulator needs to do is to certify the planning module. So that the RSS definitions could be a good start for a standardization. So either use it as is, just set up the parameters that I mentioned before, or make modifications, but standardize it. Then a certification can be validated via simulation of scenarios, like the 37 scenarios of the NHTSA crash topology. Or there's the Pegasus committee. They have their additional scenarios. So you set up a set of scenarios to certify that you are actually conforming with this RSS definition. And all of this is not data-driven. You don't need to drive a single mile, right? Because we're talking about a model-based certification. Are you conforming to the definitions of what does it mean to be in a dangerous situation? Are you conforming to the definition of what it means to have a proper response? And if you do that, we know that if your sensing is correct and there was an accident, it cannot be your blame. Okay? And then validation of sensing, that is responsibility of the technology manufacturers, just like with the false positive. So what does that mean? So far we assumed, we looked only at the planning module. We assumed that the sensing is perfect. Perfect meaning that the autonomous vehicle understands its surrounding properly. It knows where all road users are located. It has correct measurements to those road users. So it understands the environment properly. Now, how do you go and validate that? That you need to validate statistically, but it's an offline validation. And here you have also redundancy. You have redundancy by using more than one sensor modality. You have cameras, you have radars, you have LiDARs. So the amount of data driven that you need in the context of redundancy is much, much lower than this 10 to the power of 9 that I mentioned at the beginning. And this is left to the technology manufacturer in terms of how much risk are you willing to take. For example, if you are a big risk taker and you want to reduce cost, put only cameras and maybe a front-facing radar. So the probability of a sensing mistake is higher than another actor who would put cameras, radars, and laser scanners because it has more redundancy. But now it's a matter of how much risk are you willing to take, because if an accident happens and the cause of the accident was a sensing mistake, it's really your responsibility. Okay? But now it's something that every actor can decide what level of risk they want to take. Right? And this is data-driven, but this is data-driven as an offline, because it's not reactive. It's not like the planning module that every action you make, the environment acts back. So let me show you a few examples. The first one is a simulator. This is a complicated maneuver called double merge. So the red cars, their desire is to verge to the right, and the white cars, their desire is to verge to the left. And this simulator, in every trial, it puts 8 cars in random positions on a stretch of about 100 meters. And they need to satisfy their goal. And of course, they're not allowed to make any accidents. And the idea is that the planning module does this negotiation without reducing the flow of the traffic. Of course, if you now stop and try to satisfy your desire, you may succeed, but then you are obstructing traffic. So this is kind of simulators. Let me show you from some real driving. So in this clip, there's going to be a merge. And let us see here. So this is the AV car. This is the front view of what the AV car is seeing. And what it is seen here, it is going to merge in behind this car, but the flow here is very, very dense, and people are driving here at about 80, 90 kilometers per hour. So if the AV car would wait until an opening will happen, that will never happen. Right? Maybe in some countries it will, but not in Israel. Okay? So what the planning module did, and you can see this it started to accelerate. So the sensor saw this car in front. It knew that if it drives at the same speed, it will not be able to merge. It started to accelerate, reduce the gap to the car in front, and then slide in. Right? So this is an example of assertive driving, and the RSS is integrated into the planning module. So the planning module in our test vehicle cannot cause an action that will violate the RSS. Let me show you another example here. In this example, the AV car needs to exit on the right, and the traffic is very, very dense. So again, if it waits for a gap that it can safely go in without any of the other road users changing their behavior, it will not happen. You need to squeeze in, assuming that the car behind you will slow down under the RSS definitions, and this is what is happening here. It's getting in, and the car behind slowed down in a moderate way in order to allow it to get in. Otherwise, this kind of maneuver could not have happened, and the car would get stuck and obstruct traffic. Another situation here in very dense traffic, you can see kind of the density that is happening here. You see it here, and the car needs to start moving to the left, and you'll see that it is doing it in a very assertive manner. And again, this is all under the RSS definition, so it is done in a way that is very, very safe. So final words on safety. Here we're talking about guarantees. The idea of this model is to start a conversation using formal methods. Right? I'm not talking about philosophy. I'm talking about formal methods, scientific methods, in order to create a transparent model that would provide guarantees of the planning module. It's not just about formalizing the law, because a car is allowed to violate traffic in order to escape an accident. That means if I'm driving and I see someone is going to hit me, and in order to escape the accident, I need to cross a solid line, I'll cross a solid line. Right? What I'm not allowed to do when I'm doing my actions is create another accident. Okay? So what this model really says is that I can do whatever I like to do as long as I don't cause an accident. I'm allowed to violate traffic laws, but I'm not allowed to cause accidents. Okay? And this also provides a context also for ethical dilemmas, for ethical decisions. So in the way we designed it, there are no ethical decisions. I'm simply not allowed to cause accidents. Right? But one can add ethical considerations. Let's assume that a regulatory body in some country, in some city, comes and says, in order to escape an accident, you're allowed to cause another accident. The reason that in our model we did not allow it is because we say that our decision-making of accident severity is not objective. It's very subjective. Because I see an accident is coming upon me, and I see another car, and I tell myself, if I hit that other car, overall situation will be better, because it's a milder accident. But what I'm not aware of is that in that other car, there's a baby in the back seat. Okay, so that that there's missing information. This is why we say that the model should not allow you to cause accidents. But let's assume that the regulatory body comes and says, I will define a certain set of conditions. Under those conditions, you are allowed to cause an accident. But then under the RSS, what we can set up is a blame transitivity, that the blame would be assigned to the agent that started the chain of events. We did not put it in our model, but this is part of a conversation that can be done in order to put ethical dilemmas in the context of RSS. And as I said, in the end, that all of this will benefit from intimate collaboration with regulatory bodies, which is something that we are doing. Okay, I think this is the end. Thank you.